In this video, we're going to discuss the radius and interval of convergence of a power series. We know that power series come in two different flavors. We have those that are centered at x equals 0, and those power series can be written in the form sum n equals 0 to infinity of c sub n times x to the n, where c sub n will just represent constants for each value of n, and those are the coefficients for our power series. We also have power series centered at a different number, x equal a, and these have the form sum n equals 0 to infinity of the coefficient c sub n times x minus a to the nth power. We can think of a power series as a function in terms of the variable x. When we substitute a real number in for x into our power series, we obtain a standard series which we know either converges or diverges. Some power series will converge for every value of x. However, typically, a power series will converge for some values of x and diverge for other values of x. And so one natural question to ask about this type of behavior is, for which values of x does the power series actually converge, and for which values does it diverge? One important thing to keep in mind during any calculation involving the convergence of power series is that a power series always converges at its center. Here we have a general power series centered at x equal a, the sum from n equals 0 to infinity of c sub n x minus a to the n power. And if we take x equal to a, the center, and substitute that into our series, so we're substituting an for the variable x, what we obtain by writing out several terms is the number c sub 0, the zeroth coefficient, plus c sub 1 times a minus a, we're replacing x with a here, plus c2 times a minus a squared, and so forth. So this will be enough to see what's going on, because here we see that in the second summand here, I have an a minus a, which is equal to 0. And in the third summand, I also have an a minus a, which is equal to 0. And every other term in our power series will have a factor of a minus a raised to a power, and all of those expressions will always be 0. And so after all of the zeros are computed and added on, our final sum is just c sub 0, which is a number. And therefore, this particular series, this general power series centered at a, is seen to converge to the coefficient c sub 0 when x is equal to a. And in particular, this means that our power series always converges at its center. And note that by letting a equal to 0 in this example, we get the exact same result for a power series centered at 0. Since this is the case, we now ask ourselves, for what other values other than the center does our power series converge? And here's where it depends a bit on the power series. Some power series will only converge at the center. Some power series will converge at an interval centered around the center, and other power series will converge for all real numbers. We now make these three different cases more explicit and formal. If we're given any power series, it can be shown that the power series satisfies exactly one of the following three statements that pertain to the convergence and divergence at various values of x. Statement 1 is that the power series converges at the value of x equal to a, and it diverges for all x not equal to a. Note that x equal to a is the center of our power series, and therefore statement 1 is just saying that it converges at the center, but at no other point. Statement 2, the second option, is that a power series could converge for every real number x. And statement 3 is the most complicated of the three, and we can restate it in a more simplistic way, which we'll do in a moment, but we're writing it in this more complicated way involving inequalities for a particular reason that we'll see later. Our third case says that there exists some positive real number r for which our power series will converge whenever x minus a in absolute value is less than that number r, and the power series will diverge whenever the absolute value of x minus a is greater than r. And so here we're thinking about this absolute value of x minus the center and whether that is less than or greater than this given number r. Also note that in this case that when the absolute value of x minus a is equal to r, the series may converge or diverge. And so typically when we're in this case, we're going to actually have to check those two possibilities when the absolute value of x minus a is equal to r, which means x minus a is equal to r or x minus a is equal to negative r. We'll have to check those two cases separately using the various convergence tests that we've seen. We can restate statement 3 in a more simplistic way by analyzing the inequality, the absolute value of x minus a less than r. Statement 3 says that the power series will converge when this inequality is true. And so we can simply solve this inequality for x to determine a different way, an alternative way of stating the same fact. So whenever we have an absolute value inequality like this, this indicates that x minus a, the quantity inside the absolute value, must be less than r, but also it must be greater than negative r. And so x minus a has to be between negative r and positive r. Now, in order to solve for x in the middle of the inequality, we can add a to all three parts. And so we get the inequality that a minus r is less than x, which is less than a plus r. Remembering that a is just a fixed number, it's the center of our power series, and r is given to be a real number in this particular part. Saying that x is in this interval is another way of saying x is in the interval from a minus r to a plus r. And what we notice is that this is an interval that is centered at a. Whatever value of r is, we know that a minus r is r units smaller than a, and a plus r is r units larger than a. And so right in the middle of these two endpoints lies the number a, and this is one of the reasons why we call the value a the center of our power series. Because when our convergence is an interval here, that center is the actual center of our interval. Here is a graphical depiction of cases 1, 2, and 3, showing on a number line where our power series would converge and diverge. In case 1, where the series converges only at the center, we see that it's converging there at the number a and diverging both when x is greater than a or smaller than a. In case 2, our power series converged everywhere. And in case 3, we saw that our series would converge when we are between a minus r and a plus r, and that it would diverge when we're either bigger than a plus r or smaller than a minus r. Note that at the values of a minus r and a plus r, our power series might converge or might diverge, and so the convergence is generally unknown. Notice that these are the values where the absolute value of x minus a equals to r, and these are the values in which we need to check separately whether our series converges or diverges at those particular points. Now that we've seen that every power series converges in one of these three ways, either at a single point, at all real numbers, or at some interval around the center of our power series, we can discuss more formally the set of values, a set of real numbers, for which our power series converge, and we give this set a name. Given any power series, we define the interval of convergence to be the set of all real numbers x where the power series converges. This means that the interval of convergence consists of the values that can be substituted in for x to obtain a convergent series. We know that there are three different types of convergence for a series, and for each of the types, our interval has a very particular form. In type 1, we know that the power series only converges at the center, and so we can represent that single point as an interval of the form a to a. This is kind of an unusual way to write an interval. because typically we want the endpoints to be different. But if we want to represent a single point as an interval, this is one approach and one way we can do that. In case 2, we have power series that converge for all real numbers, which we can represent as an interval in the form negative infinity to infinity. And in case 3, although not initially defined in this way, we were able to see that the inequality condition showed us that it would converge between a minus r and a plus r, and we have to check the endpoints to determine whether those are included or not. And so our interval of convergence would have one of these 4 particular forms. Notice that all of these intervals have the same left endpoint, a minus r, and the same right endpoint, a plus r, and the only difference between them is whether or not the left and right endpoints are included or excluded. Once we have the interval of convergence, a related concept is that of the radius of convergence, and this gives a measure of the size of the interval on which our power series converges. In particular, the radius of convergence is simply the radius of the interval of convergence. The radius of an interval is the distance between the center of the interval and one of the endpoints. So in case 1, where our interval of convergence is a single point, the radius of convergence would be 0. There's 0 units between the center of our interval A and either of its endpoints, which is also A. For case 2, when the power series converges everywhere, our radius of convergence is infinity, because our interval here is infinite in both directions, and therefore the radius of that would also be an infinite value. In case 3, where we have a finite interval centered at A, we're looking at the distance from A to either of the endpoints a minus r and a plus r. And notice that by definition of these expressions, the distance from A to either of these endpoints will always be the number r. And so the radius of convergence here is the value of r that must exist in case 3. So to find the interval and radius of convergence for a particular power series, the typical approach will be to apply the ratio test to the power series. In particular, this means that we want to compute the value of r, which we define to be the limit as n approaches infinity, of the absolute value of the ratio of consecutive terms a sub n plus 1 divided by a sub n of our power series. Notice that the value of r here will often involve the variable x. Unlike in previous cases when we applied the ratio test to a particular series where we obtained a number, here we'll often obtain some kind of expression involving the variable x. The goal here is to determine for which values of x our power series converge, and therefore since we're using the ratio test, we would like to know for which values of x is r less than 1, since r being less than 1 is the condition for convergence in the ratio test. So we set our inequality r less than 1 and solve this for x. This gives us the set of all values of x for which our series converge, which is our interval of convergence. Note that when we're in case 3, that is, we have a power series where the interval of convergence is a finite interval surrounding the center A, we do need to check the 2 endpoints of that interval separately to determine whether the power series converges or diverges at those endpoints. We can do this by taking the 2 values for the endpoints, substituting them one by one into our series for x, and doing so will result in us getting an actual series. It won't be a power series anymore because there will no longer be a variable. We'll have a series with a term involving just constants, and we can use all of the various convergence tests, such as the limit comparison test, or the root test, or the integral test, to determine whether that series converges or diverges at that particular value of x.